Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face Trending List, published on January 8, 2026, just yesterday. It introduces the first deep reinforcement learning framework for nighttime color constancy, achieving a median angular error of just 1.98 degrees with only 5 training images. The paper is titled RL-AWB, Deep Reinforcement Learning for Auto-White Balance Correction in Low-Light Nighttime Scenes. And as we will see later, the results for cross-sensor generalization are really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 illustrates the core concept by contrasting traditional manual tuning with the new RL-AWB approach. In the top panel, we see the traditional workflow where a human expert must manually adjust algorithm parameters to correct the white balance, a process that is slow and often requires ground truth data. The bottom panel reveals the proposed framework, where a reinforcement learning agent effectively replaces the human expert. This agent analyzes the image's histogram features and dynamically tunes the parameters over several steps, minimizing the error iteratively, as shown on the right. Well, Figure 2 details the complete architecture of the RL-AWB framework. On the left, inside panel A, the system runs the SGP-LRD algorithm, which analyzes the raw input to detect salient gray pixels for illumination estimation. This visual data feeds into the soft actor critic agent on the right, specifically the policy and value network shown in panel B. The agent then samples actions in panel C to decide exactly how to tune the statistical parameters. Finally, panel D applies these precise adjustments, updating the sampling percentage and Minkowski norm, which refines the algorithm for the next processing step. So, to properly evaluate this cross-sensor capability, the authors introduced a new dataset called LEVI, which stands for Low Light Evening Vision Illumination. Figure 3 presents sample images from this collection alongside their ground truth annotations. The first and third rows display the actual nighttime scenes, capturing complex mixed lighting and high ISO noise. Directly beneath them, the black and white rows show the corresponding binary masks. These white rectangles identify exactly where the color checker chart is located in each frame, providing the reliable ground truth needed to train the model effectively. Alright, following the dataset introduction, Table 1 presents the quantitative evaluation. It lists angular error metrics for both the NCC and LEVI datasets, where lower values mean better color accuracy. The top half covers statistical methods, including the author's own SGP-LRD algorithm, which performs competitively. But the most impressive results appear in the bottom half under learning-based models. Here, the RL-AWB framework achieves a median angular error of just 1.98 degrees on the NCC dataset, clearly surpassing all other approaches. While the previous results focused on familiar data, Table 2 challenges the models with cross-sensor generalization. Here, the left section displays results when training on NCC and testing on the unseen LEVI dataset. Most deep learning baselines struggle significantly in this scenario, often yielding errors above 9 degrees. However, the bottom row shows that RL-AWB maintains remarkable stability, achieving a median error of only 3.03 degrees. This robust performance continues on the right side, confirming that the framework learns physical illumination properties, rather than just overfitting to specific sensor characteristics. So, Figure 7 visualizes exactly how this auto-tuning process unfolds step by step across 4 representative nighttime scenes. The leftmost column displays the raw input images, which often suffer from severe color casts, such as the heavy green tint in the first row. As we move to the right, we see the agent's progressive corrections, where the angular error, shown in white text, steadily decreases from the initial statistical estimate. For instance, in that top row, the error drops significantly from 6.44 to a final value of 1.92. Finally, the scatter plots on the far right track this convergence in color space, showing the blue estimate dots moving iteratively toward the red ground truth target. Wrapping up, 2 key takeaways stand out. RL-AWB successfully bridges the gap between statistical stability and deep learning adaptability. By using reinforcement learning to dynamically tune a traditional algorithm, it achieves state-of-the-art accuracy in difficult nighttime scenes, even with minimal training data. This highlights the potential of hybrid systems to solve complex imaging challenges where pure deep learning often struggles. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.